Hey guys, welcome to chapter 11. We are going to take a little bit of a turn in this course at this point. Everything you've done up until this point has been general chemistry, inorganic chemistry. Now we're going to dive into the realm of organic chemistry. So what makes organic chemistry different is one, it's the chemistry that talks about sustaining life. So you'll start talking more about biological systems, amino acids, carbohydrates, stuff like that. And two, organic chemistry is going to look very, very different than probably anything you've ever seen. So we're going to spend much of chapter 11 just getting used to what organic chemistry looks like, how we draw structures, what those structures mean, how do you know I got to that structure. So this is the type of chapter you're just going to have to sit and spend some time with it because you've probably never done that before. But the more time you spend with it, the easier and easier it's going to become. So first and foremost, these molecules should look a little different, a little bit more complicated, a lot more going on. So organic molecules are molecules that contain carbon and several other non-metal elements. So we'll start to see the elements carbon, oxygen, nitrogen, hydrogen very often, the kinds of elements that sustain life. So the molecules that I have here on the screen are all examples of amino acids. So amino acids are certainly important to organic or biological systems. So organic molecules contain carbon. That'll be kind of the main character of this chapter, and then several other non-metal elements. So hydrocarbons are going to be the first structures that we talk about. So hydrocarbons are going to be organic compounds that consist of carbon and hydrogen only. So these are the easiest to look at, the most predictable, and then we'll start adding different elements onto these carbon atoms, replacing hydrogens with different elements. But we'll certainly just start with hydrogens because they're the easiest. So here we see multiple ways to show different structures. So here we see our dot structure. Let me get my pointer here. Our dot structure. So these electrons are being shared between hydrogen and carbon, and we draw them as dots. Here we see the same type of structure, just instead of drawing dots, we show our bonds as lines. So remember, these lines represent 2 electrons. So this carbon is sharing 2 electrons with this hydrogen. And here's just our 3-dimensional model. We haven't dealt with these in this class before, but sometimes 3-dimensional models are really cool to look at. This is what these actually look like in 3 dimensions. One of the big take-homes here, if you can drill this into your brain early, it's going to make your life a lot easier. Carbon, like I said, is going to be the main character. Carbon will always make 4 bonds. So no matter what is attached to this carbon, it will always be attached to 4 things. So carbon will always make 4 bonds. If you can remember that carbon makes 4 bonds, that's going to make a life a little bit easier. Here we see another example of a hydrocarbon. We're just getting a little bit more complicated. So one of the things that we're going to do with this chapter is we're going to start chaining carbons together. So here we see this backbone or this chain right here. So carbon, carbon. Eventually we'll have carbon, carbon, carbon. Excuse me, I got the yawns. Carbon, 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 carbon. Huge long chains. Okay, so something to start getting used to. Here we see the carbon atom. Again, it's going to make 4 bonds. 1, 2, 3 with hydrogen, and then its 4th one is with this carbon over here. So always going to have 4 bonds on it. We're going to talk about 3 different sets of hydrocarbons in this chapter, in chapter 11. So all of these are going to have just carbon and hydrogens attached to them at first. Then we'll start to get more complicated. So the 4 types we're going to talk about are alkanes. That's when the carbon-carbon bonds are just single bonds. Then we're going to talk about alkenes. So the carbon-carbon bonds will be a double bond, or at least 1 double bond. Everything else will be hydrogen. And then alkynes, where at least one of the carbon-carbon bonds is a triple bond. Everything else will be hydrogens to start with. And then these aromatic hydrocarbons. So they're going to be these like real fancy rings. If I click back a couple, this is an example of an aromatic hydrocarbon. So they're going to be these real fancy ring structures that we're going to get introduced to. So let's start with our first organic molecule. Our first organic molecule are called alkanes. Alkanes contain only carbon-carbon single bonds, and that carbon will be at first just attached to hydrogens, and then eventually we'll put other things on there. But the main thing here is all the carbon-carbon bonds are single bonds. When we name these guys, they will end in the name A-N-E. So you'll see things like hexane, pentane, methane. So all of those are ending in A-N-E. The prefix, so the meth, eth, pent, the prefix will be the number of carbons that are connected in a continuous chain. So when I say continuous chain, I mean put your pencil down and you can trace the carbons without picking your pencil up. So continuous chain will tell us what the prefix is. So again, something you might want to just spend a little bit of time looking at and getting to know. This is 5 different ways to draw the exact same structure. So I'm going to start with this structure right here. So this might be the most familiar-ish looking one. So what we see here is a carbon chain. So carbon, 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 carbon. So that's our carbon chain right here. One thing to point out is all of these carbon-carbon bonds are single bonds, right? So single bond, single bond, single bond, single bond, single bond. Okay. If I look at any carbon atom in that chain, what we'll notice is it always has 4 bonds. So this guy right here has got 1, 2, 3 bonds to hydrogen. The 4th one is to carbon. If I look at this guy smack in the middle, it still has 4 bonds, but only 1, 2 of them are to hydrogen, and 1, 2 of them are to other carbons. But if we still count them, it's 1, 2, 3, 4. Okay, so this is just a simple straight chain example. The other ones, we as chemists are lazy. So we will always find a way to condense this down or write less, take up less room. So that's what these 3 down here are, just condensed, lazy, if you will, formulas. So what we've done here is we've just taken the hydrogens and we've drawn them as H3. So this carbon right here has 3 hydrogens attached to it, and it's connected to another carbon. So I just wrote CH3, connected it to another carbon. The next carbon in the chain has 2 hydrogens, so that's where this H2 comes from, and it's attached to this carbon and that carbon, so on and so forth. So you can start with this structure here and then kind of see how we broke it down into this condensed formula. The only difference between these 2 formulas is the way that they're written. So this one's written more as a zigzag. The reason we like to write things as zigzags is if you look at the 3-dimensional structure, that's how molecules actually look in 3 dimensions. So this is the angles that they have as they start to make these chains. So very often as chemists, just to remind ourselves of that zigzag, we draw them like this. So these 2 structures are the same. This one is just zigzaggy and this one's straight. And the ultimate lazy formula, the skeletal formula here. Let me grab my pen. So the skeletal formula has a law implied in it. So each stop or each point, we're going to imply that there's a carbon there. And I don't have my pen, so please forgive me for what this looks like. There we go. Carbon. I'm doing this with a mouse. Carbon, 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 carbon. So at each point or each stop, we're going to assume that there's a carbon atom there. So that's the first assumption. The other assumption that we're going to make is, I'm trying to get a different color here. There we go. The other assumption that we're going to make is that if there is a carbon, there's also hydrogens. So this carbon has one bond to another carbon. That must mean there's 3 hydrogens attached to it. This carbon has 2 bonds. That must mean there's 2 hydrogens attached to it, so on and so forth. So this is going to imply that all of those are carbons, and it's also going to imply that the hydrogens are attached or saturating that carbon. So ultimate lazy formula, but something that we certainly use quite often. Okay. So here's just a look at these formulas again, just to kind of get to know them, spend some time with them. For this guy down here, so here's our carbon chain. We see hydrogen, 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 hydrogen. Now we're starting to see a little bit of a deviation from those hydrogens. Instead of having a hydrogen attached up here, I put another carbon atom up there. So you can start to see these molecules can get pretty intricate pretty quickly. And this one actually looks pretty messy, but if I look at the condensed, it looks a little bit cleaner. So that's another reason we use the condensed formulas. And this is something I'm going to ask you guys to do on some of the labs, is draw these formulas. Okay. So now that we are starting to see them and understand them, we're going to talk about naming them. So as I alluded to, as long as there's single bonds only, it will always end in A-N-E. And the prefix to the A and E will be dictated by the number of carbons in that chain. So here's a table from your textbook that will help you with that. Certainly something I would suspect that you guys have available to you as you're working through this chapter. So if there's only one carbon in the chain, the prefix is going to be meth. So this is methane. And then we just work our way down. So if I look at 5, so if there's 5 carbons in the chain, that would be the prefix pent. And as long as they're all single bonds, it would end in A and E, pentane. So here we see 1, 2, 3, 4, 5 carbons. That gives us pentane. If it's 8 carbons, so 1, 2, 3, 4, 5, 6, 7, 8. So 8 carbons would be octane. So certainly you'll want to have this number of carbons and prefixes near you as you're starting to name these structures. So let's take a minute to do an example. So I want you guys to write the condensed formula for the following. So the condensed formula is going to look something like this. So bringing those hydrogens in and writing a 3 or a 2. So I want you to do the condensed formula. I want you to do the molecular formula. So molecular formula is just going to be letters and numbers. So this is the molecular formula right here. So how many carbons, how many hydrogens. Skeletal formula is going to be our ultimate lazy formula. So it's going to look something like this. So just some lines. And then lastly, what's the name? So count the number of carbons, put the prefix, add an A and E on the end. So go ahead and pause the video and see if you can work through that. All right, so for the structural formula, what you're going to do is you're going to write this carbon and you're going to put an H3 behind it. So CH3, CH2, 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 CH3. So that's what the condensed formula looks like. For the molecular formula, you're just counting the number of carbons and hydrogens. So 1, 2, 3, 4, 5. So 5 carbons, and then 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 hydrogens. For the skeletal, so here's kind of how I do the skeletal structures. Again, y'all, I'm doing this with a mouse, so please forgive me for how ugly it is. For the skeletal, I always start with a dot. So there's my dot. So that's going to be 1 carbon. And I know that I have to keep drawing till I get to 5. So 1, 2, 3, 4, 5 carbons. So here's 1, 2, 3, 4, and 5 carbons. Okay, so start with a dot, that's 1, and keep drawing until you get to 5. And then what is the name? So it's 5 carbons. We have their prefix pent. All of these are single bonds, so it ends in A and E, pentane. Okay. The next thing we're going to talk about are cycloalkanes. So alkanes don't have to be drawn as lines. Alkanes can be drawn as closed structures. So instead of having an open-ended line, we can have a closed structure. So they're cyclic, is what we call those closed structures. We call them cyclic structures. Naming these is the exact same way that we just did. So prefix is the number of carbons, ends in A and E. The only thing we're going to add to this is the word cyclo to tell the viewer that it's a closed structure. So that's where we get our cycloalkanes. So here we see 2 examples that we can compare. So this is our open-ended chain. So notice that these 2 carbons are not interacting whatsoever. So carbon, carbon, carbon. That's a 3-chain carbon. So prop is the prefix, and it ends in A and E. So it's just a regular old chain. Over here, again, we see 1, 2, 3 carbons. So still that prefix, prop. They're all single bonds, so ane, propane. But what we notice here is that this is a closed structure. So I can go all the way around this structure without picking up my pencil because there's lines to ride on for the whole structure. So this is a closed cyclic structure. So we have to tell the viewer that. We have to say that it's a cyclic structure. So cyclopropane. Okay, cyclopropane. So here's some examples of some of the most common cyclic structures. So we've seen cyclopropane. Cyclobutane is 4 carbons. So propane and butane don't exist much. These are pretty strange structures. They're really small angles. Those atoms are really close together. We don't see that often. But certainly cyclopentane and definitely cyclohexane, we will see lots and lots and lots. This hexagonal structure here is very, very stable. So as we start to look at bigger organic molecules, you'll see lots and lots of hexagons. So pentane is just a 5 ring or 5 carbon ring. Cyclohexane is a 6 carbon ring. So just getting to know these, let's go ahead and pause the video and see if you can name these, and then I'll catch up to you guys. All right, so first one, we see that it's straight chain. All of them are single bonds, and there's 1, 2, 3, 4. So this first one would just simply be butane. We see this one is a closed structure. So the first thing I'm going to write on my paper is cyclo, because it's a cyclic structure. Then I'm going to count the carbons, 1, 2, 3. So cycloprop, and all of these are single bonds. So cyclopropane. This guy, holy moly, 1, 2, 3, 4, 5, 6, 7, 8. So it's just a straight chain, all single bonds, 8 carbons. So that would just simply be octane. And then again, we've got our closed cyclic structure. So I'm going to write down cyclo, count the carbons, 1, 2, 3, 4, 5, 6. So cyclohexane. hex, and they're all single bonds. Ane, cyclohexane. So there's the names of those. So that's it for the first section of chapter 11. So hopefully you guys are starting to get a little bit more comfortable with looking at organic molecules. If it's still an uncomfortable thing for you to do, I highly advise that you go to the textbook, go to the PowerPoints that I post on Blackboard, just in the regular coursework, and work through some of those structures until you get a little bit more comfortable with them. Hope you guys found this helpful.